In a previous video, we've came up with the fact that the mass of an object is equal to mass equal to gamma, the Lorentz transformation factor, times the rest mass. So that's equal to mass times m sub naught over the square root of 1 minus v squared over c squared. And therefore, if I multiply both sides by that denominator, I have m sub naught is equal to m times the square root 1 minus v squared over c squared. If I square both sides, I have m naught squared is equal to m squared times 1 minus v squared over c squared. I want to distribute, so m naught squared equals m squared minus m squared v squared over c squared. And then let's get rid of the fractions by just multiplying by everything by c squared. So I have m naught squared c squared equals m squared c squared minus m squared v squared. So the next thing I want to do is I want to take the derivative. That is a constant for a particular mass. That is a constant, so 0 is equal to here. C is a constant, so this becomes c squared times 2m dm minus, over here, I have v squared times 2m dm minus m squared times 2v dv. So at this point, I have a 2m in every expression. So if I divide everything by 2m, I have 0 is equal to c squared dm minus v squared dm minus the 2 in one of those, so vm or mv dv. And so I'm going to label that as equation 1, and we will come back to it. So scratch that. I want to do one other thing first. So we end up with, let's bring those over, v squared dm plus mv dv is equal to c squared dm. Call that equation 1. I know that work is equal to the change in kinetic energy. That's total work. Or in differential form, dw is equal to dk. Work is equal to force times displacement, so F ds, or dx, or whatever letter you happen to like at the moment. Keep that as equation 2. If we look at momentum, I know force is equal to dp dt, which is dmv dt, which is mdv dt plus v dm dt, F ds, which is equal to dk, which is equal to m dv dt plus v dm dt ds. I'm going to distribute, so this is m dv dt ds plus v dm dt ds. Do a little switching there, and so this becomes m ds dt dv plus v ds dt dm. Well, ds dt, s is the position, and the ds dt would be how fast it's going. So this becomes mv dv plus v squared dm. Call that equation 3. And that's equal to f ds, which is equal to dk. So now if we bring in equation 1, this mv dv and v squared dm, we already figured that out. That's c squared dm. So therefore, dk is equal to c squared dm. If we take this object and we start it at rest and we apply this force to it to get it accelerating, we're basically integrating. This is going from its rest mass to whatever the mass ends up being. Dk goes from 0 to k. And so my kinetic energy is equal to c squared m minus m sub naught, which is mc squared plus m naught c squared, minus m naught c squared. Therefore, mc squared is equal to k plus m naught c squared. This is the kinetic energy. This is the rest energy. And that's all that we're dealing with here. So this is equal to energy, which is mc squared, or written in a more traditional form, E equals mc squared.